Good afternoon, dear colleagues. I'm Indrabayeva Olha, and I am an associate professor of National Aerospace University, Kharkiv Aviation Institute. And today I want to introduce my topic, simulation modeling of the optimal signal processing method for onboard helicopter radar of surface elevation measurements. Helicopters play an important role in a wide range of civil and military missions. Helicopters have many advantages over airplanes. Their ability to take off and descend vertically and hover in the air without moving allows helicopters to land and maneuver in limited area, avoiding obstacles. This makes them ideal for use in a wide variety of environment. It's urban, mountains, and hard to reach or have to research area. At the same time, their use carries significant risks. For example, if a helicopter must land in unrepair areas in emergency or on demand, this can put the crew and passenger at risk. Statistics on aviation accidents around the world show that most accidents and disaster occur during landing. It is not difficult to perform such maneuver during the day in sunny weather, but landing becomes much more dangerous in poor visibility condition of, for example, snow, rain, dense fog, and smoke. Example of such maneuvers are shown on the slide, and an unsuccessful landing too. On a board device such as GPS, inertial navigation system, Doppler navigation system, and radio altimeter can be reduce the risk to pilot and crew during the voyage. At the same time, these systems are not capable to analyze the surface and planning the helicopter's landing on a flat area in unknown area. Most developers use ready-made solution in the optical or infrared range in combination with a GPS receiver or implement more complex all-weather ready systems, but using heuristic algorithm. The simplest was without solving the optimization problem of signal processing. This approach is useless. Each task must be worked out both theoretically and practically. The task of surface elevation measurement for safe landing has its own features and requires independent research. Also, it is based on a single theory of statistical optimization of radio engineering system. In connection um, with the above, the task statistical synthesis of the method and algorithm for high precision and all-weather measurement of the surface elevation of the area selected for helicopter landing using an onboard two antenna radar system and relevant to this research. Um, okay, and um, let us consider in Figure 5 the geometry of surface elevation measurement for a helicopter. H is barometric altitude that measured by a barometric altimeter above the sea level. D is a slant range from the helicopter to each point of the surface. And theta H is the elevation angle of each point on the surface. Expression 1 shows that the estimated surface elevation uh, it is necessary to measure slant range and elevation angle. Next, we consider the stages of finding these parameters. As a prototype of the radio engineering system, a two antenna sum and difference helicopters surface restoration system is used. Due to spectral diversity of the antenna in the direction of the observation area, two radiation patterns are formed. The direction of maxima of radiation pattern are displaced by a certain angle theta delta related to the given equisignal direction. The equisignal direction is assumed to be known and is set by the angle theta 0, which can be changed in time during the flight, performing a successive scan of the surface along the coordinate x. It is assumed that antenna radiates probing signals in the direction of the observation area. It is a question 2, where phi is a radiation pattern, A is a complex envelope of probing signal, and F0 is the resonant frequency. Our signal reflected from the surface is detected by two antennas. That is expression 3. Uh, show that radiation pattern cut out the area of the surface. The signal propagates to each point and return with some delay time that you can see in our unit signal. It's S0. And also we have in our scatter signal, its coefficient F from 0, it's complex backscattering coefficient at every point of observation area. Also, our angel's theta was converted to surface coordinate x at a fixed area antenna height. Considering the sum and difference signal processing in the higher frequency part, the signal at the output of sum and difference channels can be written by expression 5 and 6. To simplify the analysis, the shape of the radiation pattern is taken as a Gaussian cross without side lobes, as is shown in figure 6. The obtained expression 5x6 corresponds to the ideal situation of receiving scattering signals only within the linear section of different radiation patterns. To achieve such an effect in practice, it is necessary to find this linear part, and to this reason, strobe pulse pair uh, are also added to the received signals at a position with the center of equisignal direction x0. After some indifference processing, the signal are sent to receiver where internal noise added. The observation area, the observation equation to be further processing has the form of equation 9. Based on the observation result, it's necessary to optimally estimate the position of the center of the linear part of the different radiation pattern corresponding to the delay time, the range to each surface point, and the duration from the equisignal direction theta x, which is converted into viewing angle theta. The result of the range and angle estimation are then converted to the surface elevation chosen by the pilot for landing using Formula 1. To obtain the optimal algorithm for estimation the lambda parameter, we use the maximum likelihood method. We construct a likelihood function and obtain the system of likelihood equation. The feature of this system is that it does not calculate the ordinal or and partial derivatives of the likelihood function, but uses the mathematical apparatus for calculating the variation derivative since the range and angle parameters like a function of coordinates. As a result of solving optimization problem, three algorithms are obtained. The first estimates the position of the slope pulse at time, which is the sum of the result of the coordinates filtering of the observation equation in the k sum and k data filters. These filters they are different for different channel. Knowing the position of the center of the strobe pulse, the distance to each point of the surface is estimated using algorithm 13. The main operation on the received pulses observed in linear part of the different diagram in the convolution with a reference function in the form of the amplitude of the strobe signal delay in the time by 2d divided by c. Intensity to estimate the angular position of point on the surface. Only signal from the different channel is used, where the convolution with the reference function is also performed. This can be seen on the slide in the expression 14. That is, we can recover not only the central point, the point of the equisignal direction on the surface, and determine the height at this point, but we also can estimate all the points that fall within the linear area of the discrimination characteristic. Then analyzing the optimal operation, we developed a block diagram of the optimal terrain elevation methods. Okay. Here is a block diagram of the main components of the onboard radar that measured the height of the surface under the helicopters. Almost operations are considered in the algorithm except for three blocks. This one, and this one. There are processing units that converted the measured amplitude into parameters to be evaluated. That is, these are discriminating characteristics used to recalculate the optimal output effects of the parameters value. In order to verify the performance of the proportional method of surface elevation measurement, simulation modeling is carried out in MATLAB. Assuming ideal measurement condition, a flat surface model, a constant value of the reflection coefficient, and radar cross section of the surface in all direction and all coordinates. Ideal radiation patterns that form perfectly linear section of the directional finding characteristics. The result of the simulation are shown on the slide. On a flat surface, the error is no more than 30 centimeters, and with various in height, it does not exceed 1 meters. As a result of the simulation, uh, distorting are observed, and it is not possible to restore the relief for harmonic changes. That is due to significant irregularity of the terrain within the radiation pattern, and this case is not taken into account in the problem statement. Also, the same simulation are carried out for two-dimensional surfaces. Yes, it is not possible to restore the geometry perfectly, but any terrain distortion will be clearly visible on the pilot's screen. And as a result, the mathematical model of the optimal signal processing algorithm two antenna amplitude sum and difference radar system for measuring surface elevation from the helicopter is developed. Also proposed the block diagram of the radar system and the simulation modeling is performed according to this optimal algorithm. And like result, simulation shown that and the flat surface, the role is estimation the surface elevation is no more than 30 centimeters, and when varying, it does not exceed 1 meters. Thank for your attention. That's all.
Okay, thank you for your report. Dear participants, do you have any questions?
Thank you indeed. Yeah, it's all right. You have right.
Okay. Olha, can you say, is there any dead zone for the system?
I can hear you. Can you please repeat?
Is there some dead zone for radio wave radiation, or like meter or
That's
2, or dead zone where we can see the result?
Yeah, as we use impulse method, we have some dead zone, but it's on a low, low height, low altitude when we flying on low altitude. But we consider that our helicopter system it's like moving to the some um, altitude. It's almost 1.5 kilometers. Scanning it, and after this, analyzed this surface to planning the landing.
Mhm. So thank you. Understood.
Thank you for question.
Thank you very much. So we are approaching the last